Hello and welcome. Set theory. A set is a collection of objects and ordered elements. We use capital letters to give names to sets, and we use small letters to give names to the elements of the set. And we say here small a is an element of a set A, or we say A belongs to A, an element of A, or sometimes in A. And when if it's not, we say A is not an element of A is not in A. The size of a set, it's also called the cardinality of a set, is the number of elements in the set. If the set is finite, that would be the number of elements. Otherwise, it's infinity if A is infinite set. Here are some examples. V is the set of vowels, and as you see, it has 5 elements. So the size of V, or the cardinality of V, is 5. And we can clearly say A belongs to V, but X does not belong to V. Sometimes we use several ways of defining a set. Here, O is the set of odd positive integers, and the size of this set is infinity. Here's we use this as we say this as a set builder notation. So we are building the elements of the sets as we go. So n is 2k is of the form 2k plus 1. K is an integer greater or equal than 0. So these are the same. This is the same set of the odd numbers. So when you put k0 here, you get 1. When you put k1, you get 3. When you put k2, you get 5, and so on and so forth. Here's an example of a set k in z greater than 1, k less or equal than 100. This is the set of integers from 1 to 100, and the size of this set is obviously 100. Here's another example. We can say this set is of the form, or its elements are of the form 1 over n, n belongs to z greater or equal than 1. So obviously this set is 1 over 1, 1 over 2, 1 over 3, etc. Or the same set here, we can also use this notation to define this set. We say 1 over n, n equals 1, 2, 3, 4, etc. Here are some useful sets that are used quite a bit in discrete mathematics, particularly. Z is the set of integers. N is the set of natural numbers, which is the non-negative integers. Q is the set of rational numbers. It's the set of form fractions, P over Q. P and Q are integers, and Q is different than 0. Obviously, n z greater than 0 is equal to the set n. N plus is z greater than 0, which is 1, 2, 3. It's the set of positive integers. R is the set of real numbers. We will be using these sets quite a bit. Here's an interesting set. It's called the empty set, and we use this notation for it, or this one here. So the empty set is a set with no elements. And obviously, the size of this set is equal to 0. Here are examples of empty sets. N is an integer. N squared is equal to 7. You can't find an integer, you square it and you get a 7. It's an empty. X in R, x squared plus 1 is less or equal than 0. Again, there are no such real numbers. If you square them and add 1, you get a negative number. N is an integer, is a natural number, N is even and prime. That's impossible. N cannot be at the same time even and prime. Here is something that we need to define is subsets, and we use this symbol to identify those subsets. So we say A is included in B or a subset of B if for any x, if x in A, then x in B. So you see, you can make this sketch here. A is inside B. Any element of A is element of B. Here are some properties. If A is included in B, and this symbol is and B included in C, then A will be included in C. A included in B, B included in C, then A is included in C. Now, also, for any set, A is included in itself, and the empty set is included in A. Here are some examples, some other properties. If A included in B and B included in A, then A is equal to B. So down the road, if you want to prove that two sets are equal, you need to prove two things. You need to prove A included in B and B included in A. When we say A is not included in B, this means there is, at least this symbol means there is an X in A and X not in B. So you see this example here. A is 1, 2, 3, B is 2, 3, 4, 5. Now, obviously, A is not included in B because 1 is in A and 1 is not in B. Now, you can say proper subset, strictly included. So we say A is strictly included in B, which means A is included in B and A is different than B. Here is an example of this situation. A is 1, 2, B is 1, 2, 3, 4, 5, and obviously A is strictly included in B. The power sets, and we use this symbol for it. Power set of a set S is the set of all subsets of S. So now in this example, S is 1, 2, 3. Now all the subsets of 1, 2, 3 are empty, is always there, and the set itself is always there. And you have 1, 2, the set with element 2, 3, 1 and 2, 1 and 3, 2 and 3, and 1, 2, 3. If you count those, you find 1, 2, 3, 4, 5, 6, 7, 8 of them. And so the size of the power set of 1, 2, 3 is 8, which is 2 to the power 3. You have 3 elements here, 2 to the power 3. So in general, the cardinality of PS is 2 to the power the cardinality of S. So if you have 4 elements in S, you will get 16 elements in the power set. So you'll have 16 subsets of S. The Cartesian product A times B is a set of ordered pairs xy, x in A, and again this is and y in B. So example, let A be 1, 2 and B be 1, 2, 3. Now if I want to multiply A times B is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. And as you see, we're not multiplying 1 times 2. We're not multiplying 2 times 1. We're not multiplying these numbers. We are ordering them in pairs. So A times B is this set, and B times A is now the other way around. B times A, so 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2. And you see they're not, those two sets are not the same. And then what is A times A? You get 1, 1, 1, 2, 2, 1, 2, 2. Now here are some properties. You notice here we have 2 elements here and 3 elements here. The product will be 6. 1, 2, 3, 4, 5, 6. So the size of A times B is the size of A times the size of B. The cardinality of A times B is the cardinality of A times the cardinality of B. Now, if A times B is equal to B times A, then A must be equal to B. Otherwise, they're not equal. And easily we can see if A is included in C and B is included in D, then A times B will be included in C times D. Let's take some examples here. 1 belongs to the set 1, 2, 3? Yes, because this element is right here. Now, 1 is included in this. That is false because this only treats sets. This is not a set, so you can't do that. Is 1 included in this set? The answer is no, because this is the number 1. This is a set with containing the number 1. So that is not true. Here, is this true? I will look at the elements here. This one, I find it here. Yes, it's true. Now I can write this belongs to this as well, because as a whole, I can see it right there. As a whole, I can see it right here. So that's true. If I have a set with 1 element, which is the set of 1, is this included in this? The answer is no, because you need to take this. Where's this? Oh, here we go. Here we go. You need to take this as a whole and see, do you see it inside here? You don't, then it's not included in, then this set is not included in this. Here, is 0 in empty set? No. Is empty set has no elements, but you can say 0 is an element of it. Is this true? You look at that, it's inside here, yes. Is this true? Yes, because the empty set is included in any set. Is this true? Again, no, because this as a structure, you don't see it inside here. Now, obviously, if I put here like that, then it will be true. But as it is now, it's not true. Here, is this true? I look at this here and I see it right there, so it's true. Is this strictly included in this? The answer is no. Those are equal sets. Yeah, this is not strictly included in this. Now we go to set operations. The first one is the union, set union. So you have 2 sets, A and B, and we say A union B is the set of elements X in A. This one is or X in B. And A union B is the shaded part of this. This is A and this is B, and all of those are A union B. We'll take some examples down the road. The intersection. The intersections of 2 sets is those elements that are in both sets. So X in A and X in B. You see, this is the shaded area is the A intersection B. A minus B. A minus B are the sets of elements in A, but not in B. So this piece here is A minus B. This piece here is B minus A. In the middle is A intersection B. Now, clearly you see that the union, all of these are A minus B, union B minus A, union A intersection B. That's an interesting property to remember. The complement of a set A. Now, I need to say that normally we work with sets that are part of a big set is called a universal set. So this big square here, big rectangle here is a universal set, and that's A. So A, sometimes we call it bar, or this complement of A is this shaded area. Now you see that if I have union of A and the complement of A, I get the whole big set. And you know that these two sets are disjoint. Disjoint means their intersection is empty. Two sets are called disjoint if their intersection is empty. Set partition, basically you have a set and you cut it into pieces. Each one of these pieces is not empty. Any two of them are disjoint. And if you have the union of all of them, you get A. Pretty kind of straightforward. And here's an example, 1, 2, 3, 4, 5, 6. So this is one example of partition. This is another example of partition, 1, 2, 3, 4, 5, 6. This is another one, there's a whole bunch of them, 1, 2, 3, 4, 5, 6, and so on and so forth. Those are partitions of the set A. Here are some important set identities that are quite used in discrete math. Those are, if you see that the complement of the complement is A, that's straightforward. A intersection the universal set is A. A union empty is A. That's easy to know, to see. A union the universal set is U, is the universal set. A intersection phi, which is the empty set, is empty. A union A is A intersection A is A. All these are really straightforward. Sorry. This is the commutative properties. A union B is the same as B union A. A intersection B is the same as B intersection A. This is associative. A union B union C is A union B union C. This is an important one, the distributive property. So A union B intersection C is A. Let's see how we can do that here. A union B and A union C, and you put the intersection. A union B, A union C, the intersection. The same thing here, you see A intersection B, A intersection C, and you put the union between them. Those are the Morgan laws. The complement of the union is the intersection of the complements. The complement of the intersection is the union of the complements. Obviously, A union A bar, or the complement of A, is the universal set, as I mentioned earlier, and A intersection, the complement of A, is empty. Now, all these properties can be proved directly, or you can use what we call membership tables. So I'm going to do one of them using membership tables to show you how it's done. So here I want to show this distributive identity. So I have three sets, A, B, and C. So I put A, B, and C. Then I put 4 ones, 4 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 1 0, 1 0, 1 0, 1 0. Now, 1 means the element is in A. 0 means the element is not in A. So actually what we are doing, we are distinguishing 8 different cases. X could be in A, B, and C, or X could be in A, B, not in C. X could be in B, C, not in A. X could be not in A, not in B, not in C. That's what we're trying to do. So what we do, we have B union C. B union C, so you have to have at least one. You get 1, 1, 1, 0, 1, 1, 1, 0. Excuse me. Then you have to do intersection A intersection B union C. You have to have A intersection this. You have to do this column and this column. Intersection, both must be 1. So you have 1, 1, we get 1, 1, 1, we get 1, 1, 1, we get 1, 1, 0, we get 0. 0, 1, we get 0. As long as you have 0, 0, you get 0, 0. And you keep doing that. In the end, you compare this column with this column, and you see that these two columns are exactly the same. So A intersection B union C is the same as A intersection B union A intersection C. Here's an example. I use here the universal set is 1, 2, 3 up to 15. So I have all of them. A is a number in between 1 and 15, which is a multiple of 2. We can say n mod 2 is 0. So A is all multiples of 2. B B contains all multiples of 3. So you see, A is 2, 4, 6, 8, 10, 12, 14. B is 3, 6, 9, 12, 15. So now easily A union B, meaning all these numbers, which means n in U, n is a multiple of 2 or a multiple of 3. Intersection is 6, 12. That means n that such that n is at the same time a multiple of 2 and a multiple of 3. Here we go. What's A minus B is this piece here. That means multiple of 2, but not multiple of 3. 2, 4, 8, 10, 14. 3, 9, 15 is B minus A, multiples of 3, not multiples of A. A minus B are those multiples of 2. We did that. Now we have we need the complement of A. The complement of A are those who are not multiples of 2. Okay, then you see like 1, 3, 5, 7, 9, 11, 13, 15. The complement of B are those numbers that are not a multiple of 3, 1, 2, 4, 5, etc. You notice in this example that the total element number of elements in A union B is 10. You count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A has 7 elements 1, 2, 3, 4, 5, 6, 7. B has 5 elements 1, 2, 3, 4, 5. Now, if you add these two, you get 12. You don't get 10. The reason being is the 6, 2 was counted twice. So the A intersection B, the size of this set is 2. And then we have this formula. A union B, the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersection B. Here are some exercises. If A union C is equal to B union C, that does not mean A is equal to B. That does not mean necessarily A is equal to B. In this case, you need to give a counterexample. You can't use the membership tables to prove this kind of properties. Counterexample, take A1, B, the set was element 2, C is 1, 2. So you notice that A union C is 1, 2. B union C is 1, 2. but A and B are not the same. If A intersection C is equal to B intersection C, again, that does not imply A is equal to B. Counter example, A is 1, 2, B is 1, 3, C is 1. So A intersection B, A intersection C is 1. And B intersection C is 1. They're the same, but A and B are not the same. Now, if both A union C is equal to B union C, and A intersection C is equal to B intersection C, then A is equal to B. And to see this, we need to prove, as I mentioned earlier, to prove that A is equal to B, you have to prove two things. You have to prove A included in B, and you have to prove B included in A. So let's start proving A included in B. So I take X in A, then by definition, X will be in A union C. So X in A union C, then X will be in B union C. Then X is in B or X is in C. Now, if X in B, then we showed A included in B. If X in C, then X in A intersection C, because X is in A and X now is in C, then X is in A intersection C. X in A intersection C will mean X in B intersection C, then X in B, then A is included in B. So we proved A included in B. You do the same thing to prove B included in A. Here's another example that I want to also go through. Sometimes you are asked to prove or to identify this set or this set, or to prove this one is equal to AN or this one is equal to A1. So you can't really solve this problem if you don't understand what these sets are. So what you need to do here, you need to replace I by 1, by 2, by 3, and try to familiarize yourself with these sets. So A1, so I is 1. So we're going to go all the way from negative numbers and stop at 1. Here we go. 2, you do the same thing, you stop at 2. 3, N, you stop at N. Now you can see what's happening. A1 is in A2, is in A3, and so on and so forth. So you have situations like this. A1 included in A2, A2 included in A3, etc., included in AN. Now it's very easily to see that the intersection of all of these sets is A1, and the union of all of these sets is AN. So anytime you have something like that, try to really understand what these sets are. And this is the end of set theory. Thank you, and see you soon.